Assalamualaikum warahmatullahi wabarakatuh. Hi guys, we'll meet again. And I think immediately we're talking about some properties of liquid and solid. And guys, hope you guys can enjoy my explanation. Okay, for the first matter, we'll talk about these condensed spaces. For the solid, where it was rigid, fixed shapes, mixed volume. And for a liquid, it was not rigid, no fixed shapes and fixed volume. Solid and liquid are referred to collectively as condensed spaces. This name emphasizes the high density of the liquid or solid as compared with the low density of gases. This difference in density is one of the most striking differences between gases and solid or liquids. The mass of air in a room of moderate size would not exceed 200 pounds. The mass of liquid required to fill the same room would be some hundreds of tons. Conversely, the volume per mole is very large for gases and very small for liquids and solids. At STP, standard condition of temperature and pressure, a gas occupies 22.4 centimeter range of cubics per mole, while the majority of liquids and solids occupied between 10 and 100 centimeters to the range of the 3 centimeter per mole. Under this condition, the molar volume of a gas is 500 to 1000 times larger than that of a liquid or solid. If the ratio of the gas volume to liquid volume is 1000, then the ratio of the distance between the molecules in the gas to the between those in the liquid is the cube root of the volume ratio, that is 10. The molecules of the gas are 10 times farther apart on the average than are those of the liquid. The distance between molecules in the liquid is wholly equal to the molecular diameter. Hence, in the gas, the molecules are separated by a distance which is, on average, 10 times their diameter. This large spacing in the gas compared with that in the liquid result in the characteristic properties of the gas and the contrast of these properties with those of the liquid. This comes about simply because of the short-range nature of the intermolecular force, that van der Waals force. The effect of this force decreases very sharply with increase in distance between the molecules and falls to an almost negligible value at distance of 4 to 5 times the molecular diameter. If we measure the force by the magnitude of the term A per molar volume range of 2 in the van der Waals equations, then an increase in volume by a factor of 1000 in going from liquid to gas decrease the term by a factor of 10 to the rank of 6. Conversely, in the liquid, the effect of the van der Waals force is 1,000,000 times larger than it is in the gas. In gases, the volume occupied by the molecules is small compared with the total volume. The effect of the intermolecular force is very small. In the first approximate conditions, these effects are ignored, and any gas is described by the ideal gas law, which is strictly correct only at P equals 0. This condition implies an infinite separation of the molecules. The intermolecular force will be exactly 0, and the molecular volume would be completely negligible. Is it possible to find an equation of state for solid or liquid that has the same generality as the ideal gas law? On the basis of what has been said, the answer must be in the negative. The distance between molecules in liquids and solid are so small, and the effect of the intermolecular force is correspondingly so large that the properties of the condensed gases depend on the detail of the force acting between the molecules. Therefore, we must expect that the equation of state will be different from each different solid or liquid. If the force law acting between the molecules were a particularly simple one and had the same analytical form for all molecules, we could expect that the law of the corresponding state would have universal validity. In fact, the intermolecular force do not follow such a simple law with precision. So that the law of corresponding states must also be expected to fall short of general applicability. It remains a convenient approximation in many practical situations. Okay, after we talk about condensed species, the next matter is the coefficient of thermal expansion and compressibility. There are the first equations. V equal V0 times 1 plus alpha T, where T is a Celsius temperature. V0 is the volume of the solid or liquid and 0 degrees Celsius. And we just say this is the 5.1 equation. So after we get the 5.1 equation, we get the 5.2 equation. This is volume equal volume 0 times 1 plus AT plus BT to the rank of the 2 plus until n. After equation of the 5.2, we get the equation 5.3. That was volume of 0 equal volume at the 0 degrees Celsius times 1 minus K. The value of the K is difference of each substance, and for the solid and liquid states of the same substance, K is the coefficient of the corresponsibility. So this is the coefficient of the corresponsibility. After times P minus 1, so we get the 5.3 equation, and that after we know about this equation, right? From equation 5.1 and 5.3, we can get an equation of 5.4. Alpha equal 1 per volume times derivation volume divide the derivation of temperature of pressure. And for the coefficients of corresponsibility, that was equal -1 per volume times derivation volume per derivations pressure of the temperature. So after we know about this equation, we can get the coefficient of the corresponsibility. This is it. So we get this equation. So after we get this equation, right, for the coefficient of the corresponsibility, we get this equation of the states for condensed spaces. So that was the correlation between coefficient of the corresponsibility and condensed spaces. This is for the equation 5.6. Volume equal volume at the 0 degree Celsius times 1 plus alpha times temperature minus start temperature times 1 minus this is coefficients of corresponsibility times pressure minus 1. So for the coefficient of the corresponsibility, this is that we get of the equations, like equation 5.6. So to the use of the equation for any particular solid or liquid, the value of the alpha and coefficient of the corresponsibility for the substance must be known. The value of the alpha and coefficients corresponsibility for a view common solid and a liquid are given in table. This table: coefficient of thermal expansion and corresponsibility at 20 degrees Celsius. So after we know about the equation, we get this table, the value of the coefficient corresponsibility, such as copper, graphite, platinum, quartz, silver, and natrium chloride. So that is for solid, and for the liquids, we get some. This is for the liquid. So the value of the coefficient of the corresponsibility, this is the table, and this is the equation for we get a value of the coefficient of thermal expansion and corresponsibility. Okay, we talk about heat of fusions, vaporation, and sublimations. The absorptions of or release the heat without any accompanying temperatures change is characteristic of a change in the state of aggregations of a substance. The quantity of heat absorbed in the transformation of solids to liquid is the heat of fusions. So fusion is the solid to liquid. The quantity of the heat absorbed in the transformation of liquid to vapor is the heat of vaporation. This is vaporation, the liquid to vapor. And the direct transformation of the solid to vapor is called sublimation. So for this, sublimation is the solid to vapor. The quantity of heat absorbed is the heat of sublimations, which is equal to the sum of the heats of fusions and vaporations. An obvious but important fact about condensed spaces is that the intermolecular force holds the molecules together. The vaporations of a liquid requires the molecules to be pulled apart against the intermolecular force. The energy required is measured quantitatively by the heat of vaporations. Similarly, Energy is required to pull the molecules out of the order arrangements in the crystals to the disort arrangements, usually at the slightly large distance of the separations resulting in the liquid. This energy is measured by the heat of fusion. Liquid composed of the molecules that have comparatively strong force between them have high heats of evaporations, while the composed of weakly increasing molecules have low heats of evaporations. The van der Waals A is a measure of the strength of the attractive force. We expect the heat of vibrations of substance to fall in the same order as the value of A. This is in fact correct. It can be shown that for a van der Waals fluid, the heat of vibrations per moles G vibrations is equal to A per B. Okay guys, thanks for watching. See you in the next video. Don't forget to like, comment, and subscribe our YouTube channels. See you. Wassalamualaikum warahmatullahi wabarakatuh.